to the CPU as far as I understand. It's honest. We'll talk about formal methods applied to the chromatic number.
Thank you, and thanks a lot for the invitation. And oh yeah.
Sorry, I wanted to make one announcement for the streamers that I almost forgot about. If you are following on the stream, the slides are available on the website. They're linked from the page of abstracts. They're hard to see on the camera. Okay.
Okay. Thanks again. Unfortunately, I was not able to be here earlier, and so I missed some great talks. And there have been, so formal methods in mathematics have been used mostly kind of in two directions. One is automated proof search, and the other one is to provide correctness. But there's actually more, and that's actually, and this problem, this chromatic number of the plane, which I talk about later, is actually some example where we can do more with formal methods technology. And the other thing I kind of want to talk about is that I kind of got obsessed also about this problem, and by talking about it, maybe more people get interested in it, and there might be some new cool results. So the overview of my talk is as follows. So first I will talk about computer-aided mathematics. So I guess there's lots of things that was already discussed the last 2 days. So most you probably know. Then I will explain this chromatic number of the plane. And so what is more what we can do in formal methods tools is what I call causal proof optimization. So, and I will explain what it is and how we can use this. And using this technique, we can then, for this problem called the chromatic number of the plane, see all kind of cool observable patterns in a certain field. Then I explain how we get these observed patterns. We can turn this into so-called unit distance graphs with chromatic number 5. Until 2 years ago, we didn't even know they existed, and now we can compute relatively small ones. And then I will draw some conclusions and present some future work directions. So first, computer-aided mathematics. So over more than 40 years, we have some great successes in automated computer-aided mathematics. The first kind of really big result was the four-color theorem. And there's the Kepler conjecture, by great work by Tom Hales. And this is Erdős discrepancy problem, which was already talked about by Keller, and which was Alexei who worked on this. And if you look at the results, so although I made the slide, so it's a bit a colored kind of image. So, but you see more and more problems solved in recent years. And one special thing is that the last 4 problems that I put here on the slide have all been solved fully automatically using SAT solvers. We already heard in the prior talk about SAT solving. So I can be brief here. SAT is short for satisfiability, and ask simply the question, formal and propositional logic, can it be satisfied? Research in propositional logic, practically solving it, goes back to the late 50s. But in the first 40 years, there have been quite some progress, but we were not able to solve formulas with more than, say, 1,000 variables and clauses. In the late 90s, there was a big breakthrough called conflict-driven clause learning. I won't talk about it, but this breakthrough and other breakthroughs afterwards allows us now to solve formulas with millions of variables and millions of clauses. If you're more interested in the details, then there is the Handbook of Satisfiability. So the version that's over there is the first edition, which is 1,000 pages. Later this year, the new version will come out, which is 1,500 pages. And there's also part of the art of computer programming. Donald Knuth wrote also 316 pages on the topic. Officially, it's just a subsection 7.2.2.2, but it's great material. Let me briefly kind of show you kind of what kind of problems we can solve with this. And this problem is so-called the Boolean Pythagorean triples problem. Will any coloring of the integers with 2 colors, let's call them red and blue, result in a monochromatic Pythagorean triple, a squared plus b squared is c squared. So on the slide I showed you the solutions for a squared plus b squared c squared with a, b, and c up to 40. And it's very easy to color them with two colors. Just if a number has an odd number of factors 5 or 7, you call it blue, otherwise you make it red. And there are all kind of easy patterns. You can color the numbers up till a certain point. You can easily do it until 1,000, 2,000, but at some point it gets hard. The best result until a couple of years ago was by Cooper and Overstreet that showed that you can color the number from 1 to 7,664. And Myers, in his 2005 PhD thesis, actually suggested that you might be able to do this for all the integers. Now, how do you do this in propositional logic? We're going to find a finite size counterexample. We're going to find whether it is not true for the numbers 1 to n. And for each number, we introduce a Boolean variable, xi. If xi is true, I is colored red. If xi is false, I is colored blue. And for each Pythagorean triple, we have two clauses, one stating that either A or B or C is red, and the other one stating that either A or B or C is blue. And so our 2016 paper, we showed that you can color the numbers 1 to 7,824, but you cannot do this for one more. And actually, the first result, you can do 1 to 7,824, can be computed in a few seconds with the right heuristics. But the latter result takes 4 CPU years. But because we were able to get high parallelization, we were able to do this in 2 days on 800 cores. And actually, if we would have had the entire cluster in Alston, we would be able to do this in less than half an hour. And the other kind of nice result of this was that, of course, the proof is big. Proof was 200 terabytes in size, but you can actually check them efficiently. And also what we heard in the earlier talk is we can now check these proofs with formally verified checkers. So when I first, so when the paper was accepted, we put it on archive. A few days later, we were contacted by editor from from Nature. She wanted to do an article on this. I had a 70-minute interview with her. I tried to explain to her the Satis school, that we can do parallelization, that we can really trust the results, but none of this made it in the article. The only central message was that the proof was really big, and that it was arguably the largest math proof ever. And then you get all these comments, like here you see, for example, 200 terabytes, that is 400 PlayStation 4s. And so, but it was not only the other kind of comments that we got. Timothy Gowers also wrote on his blog that this is possibly the most disgusting proof ever. And I met him at the Big Proof conference in 2017, and I asked him, don't you like this kind of technology? And he actually said, I really like this kind of technology. I just don't like it how you're using it. And so he actually sees that there's a lot of potential for formal methods, and he actually noticed it in kind of a free kind of technologies that he expects mathematicians would really like.
Let me stand up for mathematicians. He just doesn't like. The point is, your proof has no idea. Where's the idea? We can't see the idea.
We're going to get at this. But so first of all, this is proof assistant technology. So although many people are, I guess, working here on Lean, so I don't want to talk. It's his opinion. So he says that there's a lot of proof assistants out there, but he calls them proof whiners, because they're constantly complaining. I don't understand. Please give me more details. He would like to have more kind of push-button technology, that if you have a kind of relatively simple theorem, that you push a button and that maybe there comes a LaTeX document out of it with a proof. The other thing that he would really like is to have proof checking technology, and more in the sense that mathematicians like to do some hand waving, so skip over some details. Is there technology that can actually check things? Ideally, if there are small errors, fix it and fill in the gaps that has been done. But this talk, I want to talk about proof search, and that's also for the Pythagorean triples. There was proof search, but it was for unsatisfiability. He says, Timothy Gowers estimated about 70% of his time he wastes on trying to prove something which is false. And he says, I really would like to use the same kind of technology to find counterexamples. And not only I want to find counterexamples, ideally I want to find the smallest counterexample, because that can give me some intuition what's the next thing. And so this is also what this talk is about the small counterexamples. Okay, now the chromatic number of the plane. So for which problem are we going to do this? The chromatic number of the plane, so we have the two-dimensional space, all points in the two-dimensional space, and only one constraint. If 2 points have exactly distance 1, they cannot have the same color. And now the question is, what's the fewest number of colors we need to color all the points in the two-dimensional space? Clearly, you need at least 3 colors, because you can have 3 points with all distance 1 in between them, and that have to color differently. And if you think about it slightly more, then you can actually figure out the initial bounds that were already known in the early 50s, that you need at least 4 colors, because there are 7 points in the plane, shown over here, with 11 distances 1. This graph has chromatic number 4, so if it holds for these 7 points, it must also hold at least for the entire plane. And also there is a tiling with hexagons, the outer radius slightly smaller than 1. You can color it with 7 colors, such that in a single tile there's no distance 1, and also 2 tiles of the same color, they're more than distance 1 apart. So this was known in the early 50s, and for kind of 60 years there was no progress on this problem. And so 2 years ago, or slightly less than 2 years ago, there was the first big progress. Aubrey de Grey found a graph with 1581 vertices in the plane that has chromatic number 5. Yeah, and this breakthrough started a Polymath project, and you can go online and see there are lots of people have been working trying to improve the results. So, and actually, so when Aubrey de Grey found the graph, he contacted the media about his result. The media contacted Scott Aronson, who was also in the department in Austin where I was back then. And Scott asked, could you please check it? I have by no means able to check this. And by the way, if it's correct, you're in an excellent position to improve on this. So that's what I've been doing in the days afterwards. So I first checked it, and then I used the sub-technology, which I'm going to talk about more, to find smaller graphs. So initially, I think in a few days, I was able to get in the 800 range, yes?
So what did the Grey use to find this huge graph? Was it like a guessing mathematical approach, or was it also some computer-aided research?
Yeah, so what he did is, and I will do similar things, but others. So he had initially you make construct a very big graph, say with 20,000 vertices, and then you use, for example, SAT solver to determine that it has chromatic number 5. And he also he used other, but he also used SAT, yeah. And then you trying to shrink the graph until the property breaks. And the best thing he came up with was 1581. So, but he had construction methods. I will explain the construction methods later, and then get a big graph and then make it smaller. So the verification consists of two checks. First is that if you claim that 2 points have exactly distance 1, you have to check that these points exactly have distance 1. And so, for example, 2 points that are in most of my graphs look like this, or actually they are this. These, do they have distance 1?
This is easy. I mean, you could just use saves.
There's actually, so to do this, so we actually use Grubner basis because actually, so Mathematica, so well, actually what Otto de Grey also did and what also did, you compute this up to 1,000 decimals, and then you assume.
This is in a number field of degree 8. Just do an exact calculation in an 8-dimensional vector. We can talk afterwards.
We can talk afterward. But so actually, so it is. But so again, so the thing is, you want to do this also efficiently, right? So we have, say, 20,000 points in the plane. For each pair, you want to know this.
8 is not a big number. Yeah.
And the other.
Sorry, I interrupted. You do it to 1,000 decimal places? What's the other method?
What?
You can do it using real.
So, so what I'm doing in practice is I do this in Mathematica, do it into certain digits, and once I have the small graph, because for the big graph you don't care, but if you want to do the verification over the small graph, you actually compute it using Grubner basis, and you have the exact one. And the other check, what you need to do is to actually check that the graph that you have actually has chromatic number k. This you can do using SAT by 2 SAT calls. One asking, is there k coloring? That should be satisfiable. The other one is you ask whether there is not a k-1 coloring, which should be unsatisfiable.
The 1584, this is instant.
No. His graph, I think, is about half an hour. Yeah.
We're using a 400 GPU monster, or?
No, kind of the hardware you have in front of you. Yeah.
How many edges?
How many edges? Say, what is, I think, say on average you have, I think, 20 edges. So.
Yeah.
In this example, you just got like square roots of fractions. Is that what you've got all the time, or do you?
Yeah, no, so actually if you look at the Mathematica, actually you get the square root of the square root of the square root, right? It gets nasty. Yeah. But this talk is about more, how can we get more out of these kind of validation methods? So now we get to plausible proof optimization. Okay, so if there's so asking whether the graph has chromatic number k is, of course, checking whether there exists a coloring, but also whether there does not exist a coloring with one less. SAT solvers do not only provide the yes or no answer, but can also provide a proof of unsatisfiability. You can check this proof, and then you can see which are all the clauses that were used in the check. All the clauses that were not used in the check, you can remove, and then the problem is still unsatisfiable. Some clauses represent the vertices, and if you remove the clauses, that effectively you remove the vertices, and you get a smaller and smaller graph. Right? So this is the basic idea, is okay, construct a proof of unsatisfiability, check the proof, look at all the clauses that were used in the checking, the clauses that represent the vertices that were not used can be removed, and we can repeat. Okay, so what's actually, because there are different kind of ideas about what a proof is, so let me talk about what my kind of way of a proof, of a clausal proof, and it has all to do with redundancy of clauses. A clause is redundant with respect to a formula if the formula with and without that clause are equisatisfiable. They're either both satisfiable or they're both unsatisfiable. And what a proof is simply is a sequence of clauses that claim to be redundant with respect to the formula. And the last clause in the sequence is the empty clause. And what we're now going to do is we have the formula and the proof, and now we're going to add the clauses one by one to the formula, and every time we check, is this clause redundant with the current formula? In that case, we add it to the formula. And we repeat and repeat and repeat until the empty clause. If we are able to add the empty clause to the formula, then the formula trivially is unsatisfiable, right? Now comes the catch, okay? What we want to do here is we want to check this redundancy in polynomial time, right? Otherwise, we cannot do this. And but luckily, clausal proofs can easily be emitted from Satsovers. And what we heard about earlier was resolution proofs, and those have there's a single proof, and you cannot really reduce it. But the nice thing about a clausal proof like we have here is that you can always find different kind of justifications why a clause is redundant. So a clausal proof, which is just a sequence of clauses which is claimed to be redundant, you actually represent many, many resolution proofs. So, although we heard this before, so proof checking has been improved significantly in the last couple of years. Heuristics, how to check this proof more efficiently. Also heuristics, how to get a small core. Significant improvements regarding efficiency, but also regarding proof systems. I don't have time to talk about it, but some new proof systems allow much more compact proofs than, for example, resolution. Yeah, and so the proof of sure number 5, another hard combinatorial problem, was 2 petabytes in size, but it actually has been checked reasonably efficiently in parallel using the ACL2 theorem proving system.
This is now the largest proof ever.
This is not the largest proof ever.
Is there another nature splash?
No, I guess because also I think they figured that you just make the heuristics a bit worse and then the proof gets bigger, right? And so this is a very easier. Yeah. But the cool thing is now we have these problems that Erdos discrepancy, Pythagorean triples, sure number 5, and they all have been checked with these formally verified checkers. So we can have high confidence in the correctness. And just to give you a little bit of an impression how this kind of works, because there are actually a lot of techniques and heuristics there, we have our formula, say the blue part, and the red part is the proof that the Satshover came up with. So, and you kind of need it, it's kind of built up from left to right. One way of checking a proof is to check everything the Satshover has done, going from the first clause that the solver learned till the empty clause at the end. The other thing what you can do is you pick the empty clause and check, okay, which clauses were required to get the empty clause, and you reason backwards, right? And there are all kind of heuristics how to pull in clauses in your optimized proof. And then you get also, not only you get an optimized proof, which is the green part, you also get the orange part, which is the core. So all the clauses that were used in the proof. And so then you have your smaller formula. Yeah, and there's all kind of heuristics how to do this and actually to make the green part smaller and smaller and smaller. So one of the things what you can do is doing this multiple times. So you first have a proof, you get a smaller proof, then you get a smaller core, you solve the problem again, or in this case actually you check the proof again. So you check the proof again, but because there are all kind of heuristics in there, the checking might be completely different, and you get a smaller one, and you get a smaller one. So in what way can you actually change the proof? One of the obvious things to change in the proof is you can always swap the literals in a clause, because that doesn't change any meaning. But swapping the literals in a clause changes the heuristics. Another thing is that there is a point in the proof where a clause can be learned, because at some point it is redundant and you can check it. And there is a point where it's first used. And you can move the clause around in the proof in this interval. And so you can, once you check the proof, you can shuffle everything around as long as you kind of keep these constraints. And that way you can check again and again and again, which shrinks the proof more and more and more. So, okay, I already told it. So shuffling of clauses, you have kind of constraints. The shuffling of literals is unconstrained. And yeah, so you can, for example, do this until the proof, until there's no progress anymore, or the progress is kind of not substantial enough.
But if you, I mean, the size doesn't change if you put literals in the clause, right? So it could be that you do one step, that the size does not change, and you do that the size.
Yes. Yeah, that can happen, yeah. Yeah, and also, because so far I talked about you only have the clauses, but what also happens, so you ask, is this clause A or B or C redundant? Then you check where it's redundant, and the tool said actually A or B is redundant. So you can also, there's also literals that are removed. Yeah. And the interesting thing is that not only is the order of the clauses important for the, say, proof checking, but it also turns out that, which is well known in the SAT community, that the order of the clauses has a big impact on the SAT solver. So you can just, you have a SAT problem, you shuffle the clauses, and then it can have quite a big impact on the SAT solver. I don't want to really talk about this at this point. What I want to talk about is, say, you can have multiple different proofs, and the quality of the proof is very important how small your core gets. So if you have an efficient one of the SAT solver, which is on the left plot, then you get you can get a small core. Well, if you have a poor proof by the SAT solver, by a kind of a bad ordering, then you can have what you see is that you have a large core. And actually, so but this is more about initialization. This is not too much of a big of a point, but you can run the solver multiple times and to have a good starting point before you actually start the whole procedure. Okay, now to the important thing. So the most important slide is the next one, but I want to kind of talk about what is currently done. So you have your problem, and you construct a proof, you optimize your proof, get a smaller problem, solve it again, and repeat and repeat and repeat. So what happens is that your formula gets smaller and smaller and smaller and smaller and smaller. And there are also other ways besides proof trimming. There are other ways to do it. For example, you can randomly try to take a clause out, see whether you can reduce it. If not, you add it back, and all kind of way. But all these existing techniques, you have a formula and it gets down and down and down and down and down. What I noticed for the chromatic number of the plane is that this doesn't work. At some point, you throw out a clause and the proof gets, say, 10 times larger. You throw out another bad clause and it also gets larger and it doesn't terminate. And so this, what happens is, and that is also kind of an interesting thing, is so you, for example, what you can have, you have a formula, you get a proof, you get a core out of it, and the core talks about the proof talks about this core. Now you give this core to the SAT solver again, and now the SAT solver has severe difficulties of solving it. So it was able to find the proof when it was a bigger formula, but it has much more difficulties finding it now. And so, so the algorithm is as follows. Yeah, so what you do is, so you have your formula, solve it, get the proof, optimize the proof, or don't optimize the proof, but you get the core out of it, and then you repeat by solving the smaller formula. So the difference And this made all the difference. And so there's actually what you can see is very little difference in the pseudocode is the following. So line 5 is added and line 6 is slightly different than the line 5 of the prior algorithm. So what are we going to do? So we have our formula, we construct a proof, and we optimize the proof, get a core, so we optimize it. But then the interesting thing is we're going to optimize the proof again with the original formula. So if we have a proof for a subset of the formula, or for a subset, then it's also a valid proof for the original formula. Right? So, because everything is in there. But the interesting thing is that once you optimize your proof for the smaller one, you typically can further optimize your proof with the original formula, because there are more clauses in there. And the interesting thing is that what this allows you to do is, so what you see in practice is that the formula gets smaller and smaller and smaller, but it's not a subformula. It can actually, every iteration, you can pull clauses back in from the original formula. And what you see here is actually that the proofs goes down and the formula goes down, but it's not a subset like the existing methods. Yeah? And this made all the difference for actually getting small chromatic number of the plane, or small unit distance graphs. Okay, I don't have too much time, but let me. So we already talked about how do we construct these graphs. So there are actually two methods to build a big graph. And they are so-called the Minkowski sum of sets A and B, which all the points in A plus all the points in B, you get the Cartesian product. And so what you see here is, so for example, A is 0, 0, and so the origin and 0, 1. And B is the origin plus half and a half square root of 3. And the Minkowski sum is the one you see, the third one. And if you have just 3 colors, then the point on the left and the point on the right have to be the same color if you want to color this. How do you make a graph with chromatic number 4? You take 2 copies of it and you rotate it and you make them the left point coincide. If the points on the right points get distance 1, then you cannot color them both the same color. So as the left point, and therefore you have chromatic number 4. And so what you do in order to build these big graphs is that you take Minkowski sums and rotations. For example, so I am only going now to do the Minkowski sums. There are 2 kind of graphs I'm going to talk about, which is both are hexagons. So the hexagon, the normal, say the one with the horizontal bottom, and the one rotated by 90 degrees. And so on the left you see just a triangular grid, which you can color by 3 colors. And the interesting thing is, as soon as you take now the Minkowski sum of this triangular grid with the h prime of the square root of 3 plus the square root of 11 divided by 6, and yeah, I don't talk about how to figure out these kind of things, but if you do this, you see suddenly lots of edges appear, and the graph is no longer 3 colorable, but 4 colorable.
What are these edges? They're not all length 1.
They're all length 1, yeah.
There's a very long one.
So yeah, so on the one on the left.
The one on the left, they're all length 1.
They're
on the right, there's more than 1 length.
No, they're all length 1.
But there's some ones that are manifest.
Yeah, no. So maybe so on the left picture, you probably think that the short distance is 1, but it's 1/3, right? Yeah. Yeah, because if I would draw 1/3 only, there's no edges, right? So this is the. And suddenly if you have 7 copies of it, you see all these edges appearing. And the nice thing is you can repeat this. And if you repeat it another time, you get this nice thing that you have a 4-coloring, but that vertices that are close together, they have the same color. And if you repeat it again, then this is no longer possible, and you see other patterns emerging. You cannot really see it clearly from this graph, but if you do this 8 times, and you remove everything that is more than distance 2 from the origin, you get this graph. And all the colorings of this graph, you can clearly see lines, right? So this is the graph, and which I use now for trimming, because you can use, if you have 2 copies of this graph and you rotate it, then you can no longer color it with 4 colors. Okay. Just to kind of show what the different algorithms, so the one algorithm was reducing, 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 and the other one was the one that you actually, that you can pull clauses back in. So this is a few iterations, 5 runs. So I actually did a few thousand runs, and for many more iterations. So I think it was over 10 CPU years of computation. But the smallest one, and actually several of them, they all had 375 vertices for one part, and the rotated part had 135 vertices. And so together they form a 510 vertex graph that has chromatic number 5. And so that was able with the right method. With the left method, I also spent the same amount of computation on it, and I didn't get below 553. So what you can see is that this method actually gets you a much smaller graph. And to get back on the computation, so the Grace graph of 1581 vertices, it takes half an hour to compute that it has chromatic number 5. The graph with 510 vertices, the one shown on the slide, you can do it in 2 seconds. Right? So not only do you have a much smaller graph, you can also, checking it can be done much more efficient. Yeah? You can much more efficiently check that it's chromatic number 5. So this is 5 colors, and I put the middle one is the only vertex with the 5th color, because it is vertex critical. If you take a single vertex out, you can color it with 4. And what you see here is interesting, is that you can again see that vertices that are nearby tend to have the same color. Okay, I have to round up. So, okay, these are the conclusions, but I think this is more interesting. So far we used the chromatic, SAT technology to get a smaller and smaller graph of chromatic number 5. Hopefully we can actually use this to get to 6, under the assumption that even exists. But what about, can we also use SAT solving for the upper bound? And so there is a separate coloring of the plane where only 0.3% of the plane is colored with the 7th color. So it seems you're almost there, right? And I think, yeah, I also with 2 students, I've been exploring this now, whether we can use this to actually, can we find a coloring of the plane with, say, 6 colors? So also can we use SAT for the upper bound? And then, while I take questions, you can read a quote regarding this problem.
Okay.
Thanks so much for your attention.
Yeah, that's
What's the answer?
That's I don't know. So
I mean, by some compactness argument, this is the method, right? There will be a finite.
there will be a finite, yeah. So
The answer will be given by a finite.
yeah, if there is one of 6 or 7, then there's a finite one of 6 or 7.
That's what I'm trying to
Yeah. I have been all over the map on this question. So I really think I really thought I was very close to 6, because I had graphs for which, even if I spent many hours on it, I was not able to find a 6 coloring. And then actually I found this crazy thing is that if you what I observed, so the graph that I showed you here, this graph. So what I observed here is that every point which is an odd number divided by an odd number apart has a different color in this graph. So what I did, so I had my big graphs, which I was really hoping that it had chromatic number 6. Then I added all the possible edges of an odd number divided by an odd number to the graph, so the number of edges explodes. And then suddenly I find 5 colorings for all of them.
Oh.
So the SAT solver was not able to find it, and so I added so many constraints.
Different question.
Yeah.
You asked a much harder question.
Asked a much harder question. So I have no clue why somehow, and so I'm now actually trying to find a graph with chromatic number 6, which has these odd divided by odd edges.
You know this story about chopping up a square into an odd number of triangles of equal area?
Yeah, I know.
That's the same sort of issue. That they extend this. Yeah, they use odd numbers over odd numbers. It's the same story. They look at 2 added valuations of the real numbers.
Yeah. So what actually I'm trying to do now is trying to find the graph with chromatic number 6, which has these edges. And so there's a paper by someone many years ago claiming that the chromatic number of this must be
a different question now.
Yeah, is infinite. And so I have been able to find graphs with chromatic number 5, which has 21 vertices. I have not able to find any graph with chromatic number 6.
You understand the proof?
What?
Are you suggesting that the proof is?
No, it's just conjecture that it's infinite.
Oh, sorry, it's conjectured.
It's conjectured it's infinite, yeah. But I have been asking several people, nobody can give me a graph which is 6 or. So it's kind of very interesting what goes on. So I have been now more recently that it might be 5, but I don't know. Yeah, so it could be, yeah.
One more question, Alex?
So the operations is Minkowski sum and rotation look like very at home from very general perspective.
Yeah.
But are there any arguments, however vague they might be, that's inevitable to build these graphs in this way only? Or there might be some totally different ways of
I would, if you have a better way of constructing a big graph, I will be happy to know about it and to test it, right? I don't actually know, this method has been worked quite well, but and looking at rotations that create many edges, I don't know what other kind of construction methods might be there that might work better. So, but I'd be happy to hear about any construction methods that could help.
One more question.
So, with the two operations that you described, you were able to get these graphs. It's pretty much impossible to find, maybe not a graph that's converted to the graph with a very short description that has that 5 colorable. Do you know if, like, with only like 4 or 5 of those operations, you can actually get some graphs that work?
Yeah, it's known that you can make graphs with a few operations that work, yeah. Although proving that actually it has chromatic number 5 is costly, and there's also been a suggestion, because it's actually very compact description is there. And so if you just do one size bigger, people think it might have chromatic number 6, but it's just the graph is way too big if you just add another iteration of this. Yeah. But yes, there's small ones known that have chromatic number 5. Yeah.
Okay. Yeah, thank you.